Today, I'll be presenting the first lab for Physics 2211, focusing on constant velocity. Let's dive into how we explored Newton's second law through practical and simulated experiments. In this lab, we specifically examined an object traveling at constant velocity. Our goal was to observe Newton's second law in action and compare these observations with a computer simulation, assuming ideal conditions of no air resistance or friction. To fully understand our experiment, we relied on two of Newton's laws. First, an object in motion will remain in motion unless acted upon by an outside force. And Newton's second law, the change in motion of an object is directly proportional to the magnitude of force applied. These principles guided our experimental design and analysis. Our experimental setup involved a simple system, a marker moving across a flat surface. We ensured the surface was level, simulating an ideal scenario where the normal force equals mass times gravity. We used GlowScript for our simulation to replicate these conditions digitally. Here's a video clip showing our marker in motion. As you can see, we tracked the marker's movement using software called Tracker. This allowed us to log various data points such as position and velocity over time, which are crucial for our analysis. In our computer model, we input parameters like the initial conditions and the scale of the world in the simulation to match our real-life setup, aiming to observe how closely the model would mimic reality. Here, as you can see in GlowScript, I changed the ball velocity according to what was found in Tracker and used the model to update the position of the ball depending on the constant velocity of the object. As you can see in this model, the, the ball moves in a straight line, uninterrupted by any outside forces. And if we go to the graphs and compare the real life data with the simulation results, as you can see in these graphs, the position versus time data from the experiment shows some variability, likely due to minor unaccounted factors like slight inclines or air currents. In contrast, the simulation presents a perfectly straight line graph, indicating constant velocity without external forces. What if the x-axis was flipped? The data would still be the same, but the slope of the line would be negative because all of the values would be negative. Because the magnitude would still be the same, the rate of change would stay the same as well. Results would show about the same information. It would just appear as if the tape was moving backwards relative to the x-axis. What does this mean? Can you determine the net forces acting upon the ball? In a computer model, it is possible to make net forces equal to zero, but there's no way to prevent this from happening in real life. Friction and other forces will cause deceleration, and it is impossible to achieve constant motion outside of a computer model because there will always be forces acting upon an object. Any error in the experiment was likely human error. The marker might have moved slightly askew from the line going straight along the x-axis. There were outside forces upon the marker, such as friction and air resistance. And there could be errors in the computational data, as when we were clicking points on the tracker, the hand-tracked inputs could be slightly off from actual positions, and the actual scale might be improperly calibrated. That is all, and thank you for listening.